Okay, hello everyone. Welcome back to the online Spintronics seminar series. This is our 11th installment. The speaker today is Dr. Vivek Amin. He'll talk about the anatomy of spin-orbit torque. Dr. Amin got his PhD at Texas A&M in 2014, where he worked with Nova. And then he moved to NIST, where he was a postdoctoral associate and then a research scientist. He's been working with Mark Stiles and Paul Haney there. And this fall, he'll be joining the university with a very redundant name, Indiana University, Purdue University, Indianapolis, as a faculty member. So please welcome Dr. Amin.
Okay, Carol, thanks so much for the introduction. I just want to say thank you to Shin and Carol for organizing this seminar. I think it's been said before, but worth saying again that they've really anticipated a need to do something like this in this time and really done a great job so far. So thanks for inviting me to give this talk. So today what I'm going to do is I'm going to talk about the anatomy of spin-orbit torque. This is work that I've done at NIST with Mark Stiles, Paul Haney, and other collaborators. And so what I'm going to try to do today is give you a physical understanding of what spin-orbit torque is, and then talk about the various mechanisms underlying spin-orbit torque and what potentially new mechanisms we may consider being going on. So here's what I'd like you to take away from this talk. Spin-orbit torque is potentially low-power way to electrically control magnetization dynamics. So the typical scheme in which you consider spin-orbit torque is in a heterostructure like this, where you have a non-magnetic layer and a ferromagnetic layer on top of the non-magnetic layer. And if you run an electrical current parallel to the interface plane, you can control the magnetization dynamics of the ferromagnetic layer even though you're not running that much current through the ferromagnetic layer itself. And this control occurs via several mechanisms that involve spin-orbit coupling, and that's what a spin-orbit torque is. And so what I'm going to talk to you about today is theoretical and experimental work that indicate that there are potentially new spin-orbit torque mechanisms that we need to consider when we're analyzing our experiments. So the outline of the talk is as follows. I'm going to start off by talking about the traditional model of spin-orbit torques, which is typically thought to arise in the bulk of the non-magnet and at the interface via the so-called spin Hall effect and Rashba-Edelstein effect. And I'll also try to give a physical interpretation of what's going on here and where the promise of spin-orbit torque is really coming from. Then I'll talk in the next two sections about how we can potentially extend this model to incorporate new effects that occur both at the interface and in the bulk of the ferromagnet. So specifically at the interface, spin-orbit scattering can generate spin currents, which can exert torques. And in the bulk of the ferromagnet, spin currents can be generated where the spin direction is transverse to the magnetization, and that can exert torques at the layer boundaries. Okay, so a way of electrically controlling magnetization is going to obviously have benefits for controlling magnetic memories, and magnetic memories themselves offer several advantages. So one of the advantages is that at least the magnetic bit is non-volatile in that it can retain data when it's off and potentially radiation hard, which is important for space and medical applications. So what I'm showing you over to the right of the screen is a very cartoony picture of what such a magnetic memory might look like. So in this case, a magnetoresistive random access memory, or MRAM. And what you have is this crossbar architecture of these different bits which are made of magnetic tunnel junctions, which I'm showing over to the left. So a magnetic tunnel junction is two ferromagnetic layers sandwiching an insulating layer in between. And the idea is you can store binary information in this thing. If the magnetization of the two layers is parallel or anti-parallel, you could call that a 1 or a 0. So if you want to store information in this way, there are two things that you need to be able to do. You need to be able to read the information. You need to be able to write the information. So reading the information is fairly straightforward because of an effect called the tunneling magnetoresistance. So we know that the electrical resistance of these two different magnetization configurations, so when the magnetizations are parallel or anti-parallel, is different. and can be different by on the order of 100%. And so we have a way of reading this information, but the question then is, how do we write this information? So I won't go through the various ways in which magnetic memories have written information in the past, namely using Ørsted fields. Instead, I'll talk about the state-of-the-art mechanism of doing this, which is known as the spin transfer torque. And the way the spin transfer torque works is that if you run enough current through one of these magnetic tunnel junctions, you can change the configuration from one state to the other state. So how exactly does a spin transfer torque work? Well, what we have here is another cartoon image of this magnetic tunnel junction. And so if we run a current out of plane through this tunnel junction, the current will become spin polarized in the bottom ferromagnetic layer, which we assume is fixed either through exchange bias from a neighboring antiferromagnetic layer or because it's very thick. And so the current becomes spin polarized because as electrons flow through this ferromagnetic layer, they have majority and minority carriers of different density of states, and they undergo different scattering. So as a result, the charge current becomes spin polarized. So those spins can then tunnel through the insulating barrier in between and enter the top ferromagnetic layer, where they undergo a process called dephasing. And so the way the dephasing works is as follows. If we imagine, for instance, these incoming spins are along this direction P, if those incoming spins are not aligned with the magnetization, then once they enter the top ferromagnetic layer, they'll see this very strong exchange field and begin processing around the magnetization. So if you imagine all of these electron spins which are processing around this magnetization, the only thing that's common about all of those spins is their component of spin that's transverse, or rather longitudinal to the magnetization. So the transverse component is now going to be rotating in the plane which is perpendicular to the magnetization. And so electrons which are tunneling from different electronic states are going to have a different precession wave vector as they go into this ferromagnetic layer. And so within a couple atomic layers, you'll lose that transverse component of spin entirely. And this is what's known as dephasing. And so these spins then lose their net component of magnetization, net component which is transverse to the magnetization. And if we then look at the lost angular momentum, we can calculate that fairly easily, just using this very simple geometric principle, which is given by the magnetization cross the direction of the incoming spins. So that's the transverse component that's lost from these incoming spins. And that's what's known as a spin transfer torque, because this angular momentum has to go somewhere, so it ends up going to the magnetization. And so now if we run enough current through this device, we can transfer angular momentum to the magnetization and slowly damp the magnetization towards the direction of the incoming spins. So what I'm showing you here is an animation, which is just reiterating what I said earlier. So we have electrons which are flowing through this device. When spins enter the top ferromagnetic layer, they begin processing around the magnetization. They lose that transverse component of spin and transfer their angular momentum to the magnetization, which results in the torque. Now there's a couple issues with this scheme of controlling the magnetization and switching the top ferromagnetic layer. The first is that it can be potentially energy inefficient because you're running a lot of current through an insulating layer. So you can expect that insulating layer to heat up and to suffer losses through ohmic heating. The other problem is that if you're constantly writing a bit in this way, you're going to be constantly running a large current through an insulating layer, which can eventually damage that layer and lead to breakdown. So one potential way of addressing these problems is to separate the read and the write path. And so if you look now at the device that I'm showing to the right, we now have the same magnetic tunnel junction, but we've now put a non-magnetic layer underneath, and we're running current parallel to the interface plane. And what you'll notice is that even though you have this unpolarized current of electrons in the non-magnetic layer, they began to separate in a spin-dependent way, and that flow of spin angular momentum then flows into the ferromagnetic layer and exerts a spin transfer torque, as I showed you before. So this is one mechanism in a larger family of mechanisms, which is known as spin orbit torque. And so the idea is that now we're running this current in plane, not through the oxide layer, but we're still able to control the magnetization in the ferromagnetic layer. So how does spin orbit torque work? Well, we can talk about it from a very general perspective first. If we go back to spin transfer torque, this was really a transfer of angular momentum between two different populations. So we have carrier spins and the electrons which comprise the magnetic order, and they're coupled via the exchange interaction. And a spin transfer torque is a transfer of angular momentum between these two populations. However, if we now include spin orbit coupling into the mix, we know that carrier spins are coupled to their own orbital moments via spin orbit coupling, whereas those orbital moments are then coupled to the atomic lattice via the Coulomb potential. So through this extended coupling, we can actually take angular momentum from the atomic lattice, which is a virtually infinite reservoir of angular momentum, and transfer it to the magnetic order via spin orbit coupling. And this, in general, is what a spin orbit torque is. So this explanation that I've given you is still fairly abstract, and so I can give you an explanation or an analogy, which actually has nothing to do with condensed matter physics. It might be a little easier to understand. So in this animation that I'm showing to the right, the purple line represents the flight path that Voyager 2 took some 50 years ago as it was exiting the solar system. And you can see that every time Voyager passes by one of these planets, it undergoes this large change in its orbital angular momentum, or this kink in its trajectory. And so under no uncertain terms, what's happening here is that Voyager is stealing angular momentum from the entire planet, but it has so much angular momentum that it doesn't matter. It's a negligible difference for the planet, but it amounts to a very strong course correction for Voyager. And so the important point here is that by taking angular momentum from an external source, which has a lot of angular momentum to give, the spacecraft doesn't have to carry this extra fuel in order to make these otherwise energy expensive course corrections. And this is exactly what we're doing with spin orbit torque. We're trying to take angular momentum from this external source, in this case, the atomic lattice in the crystals, and transfer that angular momentum to the magnetization. So I've given you a fairly rosy picture of spin orbit torque. We have this gold mine of angular momentum that which we can take from, and this can potentially help make our devices more energy efficient. But as it turns out, there's both a light and a dark side to spin orbit coupling. So the light side of spin orbit coupling is that you're controlling magnetic order, so via spin currents and spin torques. And so this is essentially what I just described, where the angular momentum flow is going from the crystal to the electron spins. However, this transfer of angular momentum can go both ways. So you can also have parasitic effects like spin relaxation or spin memory loss at interfaces, which essentially correspond to a reversed angular momentum flow where electron spins are transferring angular momentum back to the crystal and thus losing their spin polarization or losing the ability to exert torques. And so an open challenge is, how do we create more of the light side, less of the dark side, and actually use spin orbit coupling in a beneficial way? Okay, so up till now, I've given a very general physical picture as to where the promise in spin orbit torque lies. And now I'll go over some of the specific mechanisms in the traditional picture of spin orbit torque. So the first one is related to the spin Hall effect, which is a way of generating a pure spin current in a non-magnetic material. So the main thing that you need to understand from a phenomenological perspective is that the electric field, the direction of spin flow, and the spin polarization are all mutually orthogonal. So in this case, for instance, if I have a voltage applied so that I have current running, say, in this direction, and for instance, say spins encounter impurity, because of spin orbit coupling, we can have a spin-dependent scattering, in this case, mod or skew scattering, which then leads to a flow of spin angular momentum in the perpendicular direction. So this is one of many mechanisms underlying the spin Hall effect, but the basic phenomenology, once again, is that the electric field, the spin flow and the spin polarization are all mutually orthogonal, which is what is allowed by symmetry in a non-magnet. And so how does this then result in a spin orbit torque? Well, if I take the ferromagnetic layer and I put it on top of the non-magnetic layer, and I run an in-plane current via the spin Hall effect, I'm going to get a spin current which flows into the top ferromagnetic layer and can exert a spin transfer torque, as I showed before. And so in this very simplistic picture of how this works, we have 100% transmission of these spins, which then result in this perfect spin transfer torque and damps the magnetization towards the direction of the incoming spins, which is in the interface plane. So there's a lot of things which are overly simplified in this animation that I'm showing you. The first thing is that spins don't perfectly transmit through the interface. There is some backflow, and that backflow can also lead to a rotation of spins, and that whole physics is essentially defined by the real and imaginary parts of the spin mixing conductance. So in addition to this, I'm also depicting a scenario in which spin orbit coupling is only important in the non-magnetic layer, which is resulting in the spin Hall effect. But when the spins enter the top ferromagnetic layer, all of that spin current gets transferred into a spin transfer torque. And when spin orbit coupling is present in the ferromagnetic region, that's not necessarily true as well. But by and large, the conventional picture has been to sort of zeroth order that the spin Hall torque is going to give you this type of damping-like torque, which results from a spin transfer torque. Now, there's another mechanism that's traditionally considered in spin orbit torque, and that's due to the so-called Rashba-Edelstein effect. And this is important at the interface between the non-magnetic layer and the ferromagnetic layer. So at the interface between these two materials, there's a difference in the work function, which leads to a very strong electric field pointing out of the interface plane. And so we know just from textbook relativity that if we have an electric field, that electric field then manifests in a different reference frame as an effective magnetic field. And so for the moving electrons, they're going to see this effective magnetic field, which is given by V cross E. So this is a manifestation of spin orbit coupling at the interface between the two materials. And ultimately, what you're going to get is this effective magnetic field that looks like the in-plane momentum cross the out-of-plane direction. So K cross C in this case. So over here in this cartoon to the right, I've drawn the interface plane and all of the different electronic states that you might expect for at least one band at the interface. And you can see this green arrow over here represents that spin orbit field. And in equilibrium, when this circuit is open, I have no net spin accumulation because all of these different spins cancel out. However, when I turn on the in-plane voltage and now run a current, even though electrons are still moving in most directions, in other words, carrier motion is still mostly isotropic, I've now biased the occupation of carriers so that I have more carriers occupied in this state, let's say, than this state. And that's what results in a current flowing in along the interface plane. But in biasing the occupation, I've also biased the spin accumulation. And so now I have this net spin accumulation, which is along the y direction once I sum over all of these different states. And so how does that result in a torque? Well, when I turn on this voltage, I then get a spin accumulation at the interface, which is constantly replenished by spin orbit coupling. And the magnetization has no choice but to then process around that spin accumulation, which gives me an exchange torque. Okay, so the summary of these two torques then is I have the spin Hall torque, which by and large is considered to damp the magnetization towards the interface plane, and this Rashba-Edelstein torque, which induces magnetization precession about that same direction along the interface plane, which here we're referring to as S. And so an open question then is the rest of the device generative or parasitic? What is spin orbit coupling doing in the rest of the device? And so I just briefly mentioned these papers here. The point of these papers essentially was to try to analyze what all of the different effects were that arise from spin orbit coupling in these types of heterostructures, but in the context of a very simple model in which we'd have plane wave scattering across an interface, and trying to understand what all the different effects are which could potentially arise from that type of model. And so I'm not going to go over all of the various things that can happen, but in the next part, I'm going to talk about what I think is the most interesting effect to arise from that analysis. And that is that the interface can generate spin currents that can then exert torques on the ferromagnetic layer. Okay, so to understand how this effect rises, we have to go from 2 dimensions to 3 dimensions. So once again, if we reconsider the Rashba-Edelstein effect, we have an interface, and we imagine there are electrons which are trapped in the interface plane. And say if an electron is moving in this direction, then that electron sees an effective magnetic field, which is given by K cross C, and it's been polarized in this sort of way. However, if we go a mean-free path away from the interface and consider, instead of just 2-dimensional scattering, 3-dimensional scattering, we now see that we can have an unpolarized stream of electrons which can temporarily interact with that effective magnetic field. and when it scatters off of the interface can become spin polarized. So in other words, this is a way of taking the physics which is encapsulated in the Rashba-Edelstein effect and making it more realistic by switching from 2 dimensions to 3 dimensions. And so the net effect is that you have a filtering of these spins, which creates an out-of-plane spin current, which is polarized. Now, there's another effect that can happen. If, say, for instance, spins are coming in from a ferromagnetic layer and they're pointing along, say, the magnetization, once they see this spin orbit field, they can temporarily precess while scattering, and that leads to an effect which we call spin orbit precession. So essentially, you have these two very basic conceptual type of things which can happen when you extend this Rashba-Edelstein picture from 2 dimensions to 3 dimensions. Okay, so here's an animation which is reiterating what I've just told you. So I have a stream of unpolarized electrons which are flowing into the interface. And you can see I have as many red electrons as blue electrons, so spins in one direction versus the other direction. And so now if you look at the reflected spins, the red spins become preferentially reflected due to this spin orbit filtering effect. Those spins then flow into the non-magnetic layer and create a spin current. So when the animation starts up again, if you now pay attention to the blue spins, they flow into the top ferromagnetic layer, they see the magnetization, and at least in the limit of no spin orbit coupling, the ferromagnetic layer began to precess and exert a spin transfer torque. So via this mechanism, you both get a spin torque in the ferromagnetic layer and a spin current which is generated that can flow into the non-magnetic layer. And when you sum over all of these different scattering events, the net effect is a spin current along the same direction as the spin Hall effect. Now, as I mentioned before, you can also have this alternate scenario where spins temporarily precess about the spin orbit field while scattering off the interface. And when you sum over all of these different scattering events, the net rotated spins are along this direction, which is partially controlled by the direction of the magnetization given by M cross S. But otherwise, the same thing happens as before. You have a spin torque which is exerted in the top ferromagnetic layer, and you have a spin current which flows into the bottom non-magnetic layer. Okay, so until now, I've given a very cartoony type of picture to expand the Rashba-Edelstein picture to see what are the other types of effects which can happen in an interface. But the next question then is, how realistic is an effect like this? And so what I'm showing you now are first principles transport calculations, which are essentially performing the same calculation as I showed before, except now taking the electronic structure into account. So there's a lot going on in this slide, but just to orient you, we have our bilayer over here. The out of plane direction is now horizontal. We have this ferromagnetic layer here is cobalt, and this non-magnetic layer here, which is copper. The electric field is along the interface plane. In this case, it's pointing into the screen. And for these results, the magnetization happens to be in the screen as well. And so what happens then is as the electrons scatter off the interface, they create these spin currents. And we're plotting the various spin currents that are created by this scattering in these two panels down here. So the first panel shows a spin current which is flowing out of the interface plane where the spins are pointing along the direction Y. So this is essentially what you would expect from this spin orbit filtering mechanism, which I showed you earlier. But we also have this configuration that's now allowed where spins are flowing out of plane and their spin direction is also out of plane as well. And so this arises from the so-called spin orbit precession mechanism. And if you look at the spin currents that I'm plotting here, you see very similar physics as the animation I showed you earlier. The spin current that flows into the non-magnetic layer seems to persist and can flow away, whereas the spin current that flows into the ferromagnetic layer undergoes this large precession and this dephasing, which can eventually result in a torque. Now there's two different curves that I'm showing here, a dashed and a solid one. So the solid one has spin orbit coupling everywhere. The dashed current curve has spin orbit coupling turned off in the ferromagnetic layer. And if you look at the dashed curves, you can see that for the most part, you get this spin transfer torque into the cobalt layer in both different spin current orientations. But when you turn spin orbit coupling on in the cobalt layer, you get two different results depending on these panels. So in this top panel, things look mostly the same whether you have spin orbit coupling on or off. Maybe it's a factor of 2, but it's not an order of magnitude difference. However, if you look at the bottom panel, this spin orbit precession mechanism seems to behave very differently whether or not you have spin orbit coupling in the cobalt layer or not. And that results from the fact that there is a spin current where the spin direction is transverse to the magnetization that is allowed by symmetry in the ferromagnet as well, and these calculations are capturing that effect. And so if I now look at the torques which are exerted in both of these cases, I find that the torque that arises from the spin orbit filtering mechanism, once again, is virtually the same whether or not you have spin orbit coupling on or off in the cobalt layer, but it can be very different for the spin orbit precession case with spin orbit coupling on and off in the ferromagnetic layer. And so that's saying that bulk spin current is also having a hand in creating a torque, which we'll talk about in a little bit. Okay, so I've talked about a simple theoretical model and first principles calculations, which are corroborating some of the physics from that model. And so now what I'll do is I'll talk about an experiment which is attempting to probe these types of effects in a ferromagnetic trilayer. And so what we have here is this ferromagnetic trilayer where the top layer is cobalt iron boron with a perpendicular magnetic anisotropy, a spacer titanium layer, and a bottom ferromagnetic layer, which could either be cobalt iron boron or it could be permalloy. And so here I'm showing the hysteresis loops from two different systems. One is a control system where the bottom ferromagnetic layer has been taken out, so you just have titanium, cobalt iron boron, and then over here we have the ferromagnetic trilayer. And so then the idea is this: by applying a magnetic field out of plane, we can then measure the hysteresis loops and see if there's an effect on the hysteresis loop when we turn on an electrical current in the in-plane direction. As you can see from the bilayer, we see no effect, but in the ferromagnetic trilayer, we see that we can actually shift the hysteresis loops depending on whether we turn on an electrical current. And so there's a couple explanations for why this could be happening. One explanation is that a spin current is generated either at this interface or in this bottom ferromagnetic layer that is exactly this spin orbit precession type orientation, where the spin current is flowing out of plane and the spins are also pointing out of plane. So that can exert a spin transfer torque in this top ferromagnetic layer and influence the hysteresis loop. Now, the other thing that can happen is the stray field from the bottom ferromagnetic layer can be influencing the hysteresis loop again. So I won't go into the details of this, but we did micromagnetic modeling to rule out that second explanation. And so ultimately, the conclusion we came to is that there is a spin current generated either at this interface or in the bottom ferromagnetic layer, which is then influencing the dynamics in the top ferromagnetic layer. So then finally, what was left to do was to take away the external magnetic field and see if you run enough current through the device, can you then use this spin current to switch the top ferromagnetic layer? And those are the results which are being shown over here. And the answer is yes, with sufficient current, you can do this. And the orientation of the polarization of the switching depends on the direction of the bottom ferromagnetic layer. So once again, this is evidence that there is some non-local control of the top ferromagnetic layer from the bottom ferromagnetic layer via spin current with this type of orientation. And here the importance is that switching ferromagnetic layers with out-of-plane magnetizations has certain technological advantages in terms of the potential efficiency for switching, and also potentially coupling different ferromagnetic layers together, for instance, for applications to neuromorphic computing. Okay, so in this final section, I'm going to talk about a third alternative in which you can have spin currents which are generated in the ferromagnetic layer, which then can flow into the interface between the two materials and exert a spin torque. Okay, so up until now, the interpretation that I've been taking has largely ignored spin orbit coupling in the ferromagnetic layer. So we're trying to understand what happens in an interface or what happens when spin orbit coupling is in the non-magnetic layer. But we've assumed that any spin current that flows into the ferromagnetic layer for the most part exerts a spin transfer torque. Now we're going to reassess that interpretation. And so the first thing to understand when reassessing that is that the symmetry constraints are quite different for non-magnets and ferromagnets. So with non-magnets, as we had mentioned before, the electrical current, the spin flow, and the spin direction are all mutually orthogonal. However, in ferromagnets, the magnetization breaks additional symmetries, especially when it's in an arbitrary direction or not along a high symmetry direction. And so that's going to lead to more allowed effects, in this case, more spin currents. So for instance, if we look at this cartoon here, in the non-magnetic region, if we turn on an electric field, we expect this spin flow where everything is mutually orthogonal to each other. However, if we have a ferromagnetic layer and the magnetization is tilted at some arbitrary angle, even if we still consider these types of Hall currents, we can still have all three spin directions being allowed and non-zero. This is what's allowed by symmetry. And so the important point here is that the spin direction not being in the same direction as the magnetization means that a torque could eventually result. So as it turns out, this type of spin current generation in bulk ferromagnets, where the spin direction is not aligned with the magnetization, wasn't very well studied previously. So in this scenario, what we're looking at here then is this type of geometry where we have an electric field, say pointing in one direction. We're going to restrict ourselves to looking at spin flow, which is in the transverse direction, but now we're going to calculate all different spin polarization directions. So in other words, we're going to look at spin currents with all of these three different spin orientations. And we're going to calculate these currents using in various mechanisms while moving the magnetization around. And in particular, we're going to focus on two different classifications of these mechanisms, intrinsic and extrinsic. Okay, so what do I mean by that? Intrinsic and extrinsic mechanisms can result in spin currents, and the way that different groups define these terms can change. And so what I'm going to try to do is be very precise about what I mean in this particular talk. And so very simply, if we think about in equilibrium what the spin current is, we're in a single electron picture just going to sum over all of the different electronic states and sum over the occupation of each state times whatever that state is contributing to the spin current tensor. And so that's what this Q sub I is. So after we turn on an electric field in linear response, we're going to get two things that are going to happen. Either we're going to perturb the occupation of carriers, or we're going to perturb the wave functions themselves, which change the expectation value of the spin current. And so very roughly, I'm going to call these things extrinsic if they change the occupation, and intrinsic if they lead to a perturbation of the Hamiltonian, which changes the expectation value of the spin current. So extrinsic contributions, for instance, could occur from impurity scattering, intrinsic contributions from the modification of the wave function. So here we're not going to look at all of the different ways in which this can happen. We're going to focus on particular mechanisms. For extrinsic contributions, we're going to stick to the relaxation time approximation. So if you're familiar with other extrinsic contributions like skew scattering or side jump, we're not including that in this analysis. Instead, we're assuming that when you turn on the electric field, you change the occupation of carriers proportional to the velocity. And from that, you can look at the different spin currents that can result. Now, on the other hand, we can look at so-called intrinsic contributions, where the electric field is perturbing the wave function, and that's characterized by the Kubo formula, which I've reproduced down here. Okay, so first let's look at results from computations of the intrinsic spin currents. So these are intrinsic spin currents, which we looked at the transition metal ferromagnets, so iron, nickel, and cobalt. And the main result is that when analyzing these intrinsic spin currents, we found that they had a fairly simple magnetization dependence. Now, one of the reasons this is nice in particular is, as I mentioned before, symmetry allows you to have spin currents in all different directions and a fairly complicated magnetization dependence. But as it turns out, we can fit the data to something which looks very much like two parts, a part that behaves like the ordinary spin Hall effect, independent of the magnetization, and a part which for historical reasons we'll call the spin anomalous Hall effect, which looks like the anomalous Hall effect as if it was spin polarized along the direction of the magnetization. So even though all of these different things are allowed by symmetry, this seems to be by and large the response that we get when we do first principles calculations in these different ferromagnetic materials. And so if we fit these particular parameters to these curves, we can then reproduce what the strengths of these different spin currents are for iron, nickel, and for cobalt with the electric field pointing along two different high symmetry directions. And what you see is that the spin currents in units of inverse ohm and inverse centimeters are fairly comparable to the spin currents that would arise from the spin Hall effect in platinum. They're somewhat less, but they're still not orders of magnitude less. So I mentioned that we're also looking at the extrinsic spin currents that can arise in ferromagnetic layers. So in this case, what we've done using the relaxation time approximation that I discussed briefly earlier is calculating these extrinsic spin currents in iron. And so what I'm showing you here is the magnetization dependence of these. So again, to remind you of the geometry, I've turned on an electric field. I'm looking at flow here in the Z direction, and I'm going to calculate all of the different spin currents that can arise as I change the magnetization direction. And what I find is something that looks like this as I go from the direction of the electric field to one particular direction transverse. And so what I see is this charge current which arises, which is only non-zero when I'm in between these two high symmetry directions. And that actually has the same magnetization dependence as the planar Hall effect. And so this is capturing a contribution to the planar Hall effect. What I then see is a spin current, which is polarized along the direction of the magnetization. And so this is like a spin polarized planar Hall effect. But you can see that the spin polarized planar Hall effect is actually stronger at some point than the charge current. And so what this means is that we are not just capturing the spin polarized planar Hall effect, we're capturing the full spin current tensor and all of the things that can then result from that. The final curve that we have here, this green curve, is a spin current which is transverse to the magnetization. And so this is another type of spin current which, if it flows to the boundary, can exert a spin torque at the interface. Okay, so this is my last slide. What I'm discussing here is an experiment which is now trying to probe whether or not we can have a spin orbit torque, which results from this type of spin current generation in a ferromagnetic layer. And so what we have here is a 32 nanometer thick slab of permalloy. We turn on an electric field, and if we do have spin currents that are generated where the spins are transverse to the magnetization, they cannot exert any torque in the bulk of the ferromagnet, again, from symmetry arguments, but when they flow to the interface, they can exert a torque. And so we could observe that optically here through polar magneto-optical Kerr effect through a deviation in the magnetization, and then using a fairly simple model, get a lower bound estimate for what the spin current had to be in the bulk, which would generate that type of deviation. And that's what was done in this experiment. And the spin Hall conductivity, which was found, was about 1,000 inverse ohm inverse centimeters, which at least agrees in order of magnitude with the calculations of the intrinsic spin currents, which I showed earlier. Okay, so with that, I'd like to thank all of my collaborators. In particular, I'm a theorist. I'd like to highlight my experimental collaborators from Korea at KAIST and Korea University, as well as NIST, Boulder, and the University of Denver. And so with that, I'll just leave you with my conclusions, two conclusions, which are fairly simple. The traditional picture of spin orbit torque requires modification. And there are two ways in which we can think about it being modified. Interfaces generate spin currents via spin orbit scattering, and ferromagnets can generate strong spin currents where the spin direction is transverse to the magnetization. And I showed some experiments which have shown some evidence that these effects exist, which could create new functionality in devices. So with that, thanks for your attention, and I'm happy to answer any questions.
Thank you very much, Vivek, for this instructive, interesting talk. So we're now ready to take questions. Alexei Kolev, please go ahead.
Hello, can you hear me?
Yes, I can hear.
So my question is about spin currents. So basically, does it make sense to spend so much effort on calculating spin currents where we know that there will be loss of this angular momentum into the lattice, as you mentioned? So maybe such calculations could give us qualitative picture, but quantitatively, we would need to also account for that angular momentum lost to the lattice.
Right, so I absolutely agree. The final picture has to be calculating the spin accumulation, however it rises, and then how that couples to create a torque. So you're absolutely right that you have these different channels of angular momentum. And so the spin current is only going to give you one sort of piece of that puzzle. Now, in terms of whether or not it's useful to do this, I think that it's useful to do this because this gives you a physical picture of what could be going on. And even though you can get a qualitative picture from it, you can still quantitatively compare the spin currents that are generated to the torques that are exerted. And that can at least tell you whether or not you can look at spin currents when you have strong spin orbit coupling, or if you do really need to think about only spin torques. And I think that in certain cases, based on first principles calculations, by and large, a spin current, say, generated from the spin Hall effect might account for a particular component of the spin torque, whereas in other cases it might not. So I think it's still useful to have this picture, at least to compare to what the full calculation of the spin torque is.
All right, okay, thank you.
Okay, thank you. Ren Chang, next question, please. You need to unmute yourself.
Oh, hello. Hi. Thanks for the very inspiring talk. So would you mind showing again the slides comparing the spin orbit filtering effect and the precession effect?
Okay. Are you talking about this one?
Probably earlier slides.
Okay.
Just a picture. Yes.
Okay.
Okay. So here, from what you draw for the for the last mechanism, the spin orbit precession, it seems that the spins inside the ferromagnets are conducting spins, and they flow towards the interface in order to interact with the spin accumulation from the non-magnetic side. So, so what if the ferromagnet is insulator? It's an insulator where there's no itinerant spins, but all the spins are localized at the moment. In that situation, is the spin orbit precession mechanism still applies?
Yeah, so you could still get theoretically a spin orbit precession effect if you had a ferromagnetic insulator. And that's because if you have electrons which are flowing in the non-magnetic layer, so assuming the non-magnetic layer is conductive, when the electrons scatter off the interface, they're still going to temporarily interact with the spin orbit field at the interface, which is going to be influenced by the exchange interaction. And so in a very simple model like this, that effect will vanish. But if you include a more complicated electronic structure, you can then get a spin orbit precession effect as well.
Okay, thank you.
Okay, thank you. I think we have some questions coming from Twitch. So Shen Fan is going to read them. Please go ahead.
Hi, Vivek. Thank you very much for the nice talk. Actually, 3 separate questions from Twitch, so I'm going to read it to you.
Okay.
The first question comes from Alice. I think she asks, which mechanism is most promising for applications?
Right.
And items are missing, if any.
Okay, so the question was which mechanism is most promising for applications, right?
Yes.
Okay, so I would say that the spin orbit precession mechanism is promising for a particular reason, that it can result in spin currents that have spin direction which is out of plane. And so if you're interested in switching perpendicular ferromagnets or driving perpendicular spin torque oscillators, which have many applications, that's something which would potentially be quite useful. At the same time, if you're interested in the spin Hall effect for any reason whatsoever, the spin orbit filtering current has the exact same orientation. So it's possible that that's something that could either help or hurt depending on what your application is.
Okay, thank you. The second question I would like to ask is also from Twitch. When you, at the beginning of the talk, you mentioned that the normal matter is the semi-infinite source of angular momentum. So what processes restore the missing angular momentum lost to spin current?
What process restore the missing angular momentum?
Yeah.
So
yeah.
Go ahead.
Yeah, so your normal matter is a kind of a semi-infinite source for spin current, for angular momentum. So if it generates some angular momentum gives to spin current, what restores that from the...
So So I suppose that kind of depends on what you mean by restoring. Certainly you can have spin relaxation where you can give the angular momentum back. So that's one way, I guess, of restoring. But this is still ultimately tied to a mechanical effect because this is taking angular momentum from the atomic lattice. So you're going to perturb the atomic lattice in some way. The idea is you're probably going to burn your sample before you ever do something severe enough in terms of taking angular momentum away from it. So that's potentially a limitation, or rather that is a limitation. But those are the ways in which you can imagine limitations, and also angular momentum going back to the lattice. Any sort of spin relaxation or spin memory loss is really the opposite of that type of effect, in very qualitative terms.
Okay, the last question from Twitch is, do you expect the same behavior to happen with thermally generated spin currents?
Yes, there's no reason why you wouldn't expect a thermal analog to these types of effects. As long as you have some sort of transport where within a mean free path from the interface, there's some interaction with the spin orbit field at the interface. You should expect a similar type of effect. Now, whether or not that is comparable to this, depends on a calculation. But in principle, you could expect something to happen.
Okay, thank you for the answers.
I'm sorry. Next question from Ren Cheng. Please unmute yourself.
Hi. So I'd like to follow up the previous question regarding the thermally generated current. So I think if you could just navigate your slide to a picture in your last section.
Okay.
Maybe in the last section.
Oh, sorry. Give me 1 second. So this is my last section. Which picture would you like?
Oh, yes.
Uh-huh.
Yeah, this slide. Right. So I think if you're gonna generate a spin current through thermal effect, such as in Vivek, spinners, or whatever, then according to the picture you're showing here and on this slide, then probably it seems that only the extrinsic contribution matters, because a gradient T, for example, can easily alter the occupation, but not directly perturb the harmonic, right? I'm not sure if I can understand from this perspective.
Right, so that's the perspective in which I was thinking as well. So if you look at this model of interface generated spin currents that we presented, that is essentially an extrinsic effect. So that comes from modifying the occupation and then looking at the scattering that results from an interface. And so all I'm envisioning is replacing the electrical current with a thermally driven current, and potentially the same types of effects can happen. But I'm not envisioning anything more complicated than that, I suppose.
Thank you.
Okay, Dongwook Go, your next question, please.
All right. Do you hear me?
Yes.
Okay, good. Thank you very much for an interesting talk. I really enjoyed to compare a lot of analogies and interesting, a lot of intuitions. So I have 2 questions. The first question is, in the field of spintronics, people always are curious how to tell in experiments what is the coming from the bulk and what is coming from the interface. And there have been a lot of trials like changing the thickness of the different layers, or I don't know, changing the growth condition and so on. So I want to hear your opinion about how we can actually access these interface contributions specifically, or maybe separate other contributions.
Mm-hmm. Yeah, so it's a great question. In a bilayer, I think it's extremely difficult. As you already mentioned, if you change the thickness of the layers, you can try to look at the intercept of certain data and try to figure out whether or not you have an interfacial contribution or a bulk contribution. I think those experiments are very hard to do, and every single data point comes from a different device with potentially different interfaces within each device as well. So I think it's very hard to do in a bilayer. If you switch to a ferromagnetic trilayer, you're obviously not looking at the same system anymore, but now you at least have one advantage, that you have a new knob. So in this case, you have two ferromagnetic layers, and the magnetization of these layers can be different, which means the interface generated spin currents or the bulk spin currents that you expect from one interface or one ferromagnetic layer are different than the other one. And so if you combine that with doing an angular dependence of the spin orbit torque, say through harmonic Hall analysis while changing the direction of the magnetization, then you can potentially access a damping-like torque, which is damping you towards one direction versus another direction. And that's something that can distinguish effects like these. And so that's what I would say, is that potentially making the heterostructure more complicated and having more knobs is one way to access these effects.
All right, thank you very much. But
so you had a second question?
Yes, I had but I have a very short question about this tri-layer structure. Do you think also there is an effect from titanium bulk in these experiments too?
Yeah, that's right.
And could you also separate them out in the experiments?
So in this experiment, there were a couple things that were done. So you're absolutely right. There was a contribution from the titanium bulk, essentially a small spin Hall contribution. And that is going to be not separable from or difficult to separate from the spin orbit filtering contribution. But in here, what I was really focusing on is this spin current. But there are ways to do it. So for instance, one of the things that was done here was to insert a very thin layer. I didn't really go into it when I was talking here, but this bottom ferromagnetic layer could be cobalt iron boron or permalloy, and both of those had an opposite response. So just like platinum and tantalum have opposite spin Hall angles, these generated oppositely polarized spin currents. And by putting a very thin layer of the other materials, so say cobalt iron boron is here, and we put a thin layer of permalloy, we're able to switch the polarization of the effect. And this thin layer is on the order of a nanometer. So it's somewhat indicative of an interfacial origin, but there's still more that would have to be done to really verify that.
Okay, thank you very much. The second question I had was, you mentioned briefly that extrinsic spin Hall effect in ferromagnet would be related to planar Hall effect like signal. And why do you think only extrinsic contribution is related to this planar Hall effect, or why not the intrinsic Hall effect, for example?
Well, in this particular case, I'm going by the magnetization dependence of the planar Hall effect. And so if you add spin to that, so you now consider a planar Hall current, which is spin polarized along the magnetization, that's third order in magnetization, right? So that's going to come from the odd response. And that's where you're tying it into the extrinsic effect. Also, at least in some of the theoretical calculations of the planar Hall effect I've seen that include electronic structure, this seemed to be the way it was calculated, looking at a relaxation time approximation. And so you can certainly get the planar Hall signal from that. And that's where the analogy is coming in. But it's just a name.
I see. Thank you.
Okay, Eric Montoya, your next question, please.
Hey, thanks for the nice talk, Vivek. At one point of clarification, when you were saying you're looking at, say, one mean-free path, are you talking about the charge momentum mean-free path or the spin angular momentum mean-free path?
I'm talking about the, so the charge, so the momentum relaxation time and then the mean-free path associated with charge transfer. So I'm not talking about the spin diffusion length or any, now the relaxation time can depend on spin. The momentum relaxation time can, but in terms of the mean-free path, that's what I'm talking about. I'm not talking about the spin diffusion length.
Okay, and a follow-up question, well, I guess a separate question, is, are you looking at extended systems, or do you have a way to know if the spin currents will lead to, say, coherent dynamics or lead to populating magnons, whether you'll have coherent magnetization dynamics in ferromagnet or not?
Right, so that's not something I have currently looked at. That's something that certainly could be done, especially if you're talking about these extrinsic currents related to the planar Hall effect. Right now, I've just looked at bulk calculations. So I have not analyzed the types of torques that they can exert, and certainly not coupled it to magnetization dynamics, which is another layer in which you have to couple to the LG equation. So that's something that potentially can be done, but not something I've looked at.
Okay, thank you very much.
Thank you. Li Junju, your next question, please. Please unmute yourself. Li Junju, we don't hear you. Please unmute yourself.
Hi, can you hear me?
Yes, we can hear you now.
Okay, very nice talk. I have a question about the spin orbit filtering effect. So when the unpolarized charge current hit the interface, the transmitted spin current will exert torque on the ferromagnet layer. But the reflected spin current has opposite spin polarization with respect to the transmitted spin current. So if the reflected spin current behave like spin Hall spin current, it will diffuse into the magnetic layer. And then in this case, the transmitted spin current and the reflected spin current will be cast out, and the total torque will be very small. Is that correct?
No, so actually these two spin currents are flowing in opposite directions. So you're right that the spin polarization is opposite, but the flow is opposite as well. So if you actually plot the spin current in a layer resolved way, the spin current is actually constant across the interface for this very simple model. And then if you add electronic structure, then they can become different. But certainly from this picture, I can see how you might come to that conclusion. But in fact, it's constant across the interface in this model, and it leads to a torque, the interface that's not canceled out by the contribution in the non-magnet.
Okay, so the reflect spin current won't diffuse into the magnetic layer anymore, because like spin Hall spin current will diffuse.
Right. So after the scattering, you'll get a spin current on one side of the interface, a spin current on the other side of the interface, and they're flowing in the same direction and have the same spin polarization. And then if you put that into the drift diffusion equations, you can then see what you might expect for the diffusion into the non-magnet.
Okay, thank you.
Okay, the next question comes from Yang Leve. Please unmute yourself.
Hello, can you hear me?
Yes.
Oh, yeah, thank you very much for the interesting talk. Actually, this is a slide I have a question on, so that's pretty good. Regarding the spin orbit precession process, is the angle of the precession also a function of, say, the depth of file or the strength of the spin orbital field?
You can think of it that way. So we've called this a spin orbit precession effect because I think it's descriptive about what's going on. But in steady state, this is still an instantaneous process. You have a spin polarization on one side, and once you have the scattering, you get a spin polarization which is now in a different direction. And you could think of that like temporarily precessing as you scatter off of the interface. And if you take that sort of physical picture, then depending on the strength of the spin orbit field and depending on how quote unquote thick the interface is, you would see something different. But ultimately, the strength of the effect is related to the strength of spin orbit coupling at the interface, if that answers your question.
Okay, that's great. Then the next question is, do you know typically how much is this angle?
So there's not a particular angle, and especially if you have a more complicated electronic structure, if you were to calculate what that angle is, it would be different for each incoming state. So I think it's probably more instructive to think of things in terms of what the strength of the effect is, but the direction is given by the magnetization cross Z cross E or Y as often is in these experiments.
Okay, so that's sort of answered by, again, sorry, next question is that, so it's pretty much impossible to make the spin rotate a full rotation or maybe multiple rotations, and you see this kind of a effect increasing then decreasing and periodically oscillating. We won't see it, right, at all.
No, the way that we're looking at this calculation, it's really more of an instantaneous effect. You're already calculating things in steady state. You're not really thinking about a time scale for the precession like that. And so you aren't going to be able to use this to...
No, let's say we have a way to tune the green vector, the spin orbital field continuously. Will we be able to even see the oscillation of this transmitted spin being, let's say, projected in the same direction for incoming spin, and then it starts to oscillate because the spin is making full rotations?
Well, I'll interpret that, I guess, to mean that if you can modify spin orbit coupling in some way at the interface, you might change the strength, but you're not really going to change the direction. I mean, I suppose you could, but you're going to change some. You're going to change the. You're going to change the spin current in some way. You could change the strength if you're modifying spin orbit coupling at the interface. That could certainly happen.
Okay. Yeah. It's too much. Thank you very much for now. Yeah. Thank you.
Okay. Thank you very much. It looks like we don't have any more questions. So let's.
Actually, sorry to interrupt, Kirill. I think there's one more question from Twitch.
Oh, okay. Go ahead.
So let me just read it. How to integrate these spin orbit torque sources in magnetic tunnel junctions for SOT MRAM application? This looks like a really application-oriented question.
So that's a great question. Let me see if I can get to it here. So if you look at this type of device structure, essentially you're going to need another ferromagnetic layer. Because you have one ferromagnetic layer plus a spacer layer, which is essentially acting like a generator of this type of spin current. But then if you want to read out, whether or not you have a 1 or 0 here, you're going to have to add the rest of the out-of-plane magnetic tunnel junction on top to do something like that. Maybe there is a more creative way of reading out what the information is through some sort of spin Hall magnetoresistance or some sort of in-plane magnetoresistance. But either you have to figure that out or you have to add another ferromagnetic layer.
Okay.
Okay, thank you. That's all the question.
Looks like that's the last question. So let's give Vivek a big round of virtual applause.